Hello everyone, my name is Renos Zabounidis, and today I'll be presenting my summer work on introspection for interpretability in multi-agent systems. In the real world, multi-agent autonomous systems require not only the ability to display precise control and decision-making in complex environments, but really the ability to compete and coordinate with other agents. And so learning optimal behavior for each agent is especially difficult due to the eccentricities which arise from the interplay between agents. And so capturing these eccentricities in a hard-coded, rule-based fashion has proved to be both cumbersome and really impossible. Success has been found in data-driven algorithms which use self-play or expert demonstrations to learn optimal behavior. The most common framework used to learn optimal behavior in complex environments has been deep reinforcement learning. Deep reinforcement learning has enabled agents to achieve superhuman performance in many tasks, including real-world robotics. This includes complex board games, as we can see here, like chess and Go, and most recently, even real-time strategy games like StarCraft 2. And then lastly, as we can see here, we have a robot which is using DeepRL in order to learn how to move to space from one box to another. And while these are all extremely impressive, these agents fundamentally are not interpretable. And this is due to the fact that they use deep neural networks, which are currently black box models. This is especially worrisome for deep multi-agent reinforcement learning agents. And so for MAIRL agents, for agents to display a deep understanding of other agents in their environment, they have to try to model the beliefs, desires, and intentions of other agents. Yet it's not relatively obvious how successful agents are at this task, as no explicit mental state of other agents is learned in training. Instead, agents must learn how to extract beliefs, desires, and intentions of other agents from the state of the world, kind of implicitly, in the MAIRL task. And so without interpretability, we're really left questioning how well MAIRL agents actually model the beliefs, desires, and intentions of other agents. Really what we've learned is that black box DBI models are not desirable in the real world. This is also just due to the fact that in many high-stakes scenarios, humans being able to understand the beliefs of autonomous agents they are working with is essential to building trust. So even if it turns out that the agent can model the human really well, if the human doesn't understand what the agent is thinking, that'll still inhibit their joint task. And so really the question then is, how do we make neural networks interpretable? Well, there's two main schools of thought in interpretable machine learning, ad hoc and post hoc models. Post hoc models attempt to provide explanations for models which are already trained. One example of a post hoc method is the saliency map, which looks at the weights of a neural network and calculates which inputs most contributed to a prediction. Saliency maps are problematic for well-known reasons. They provide very similar explanations for multiple classes, and often none of them are ultimately useful. And this is really a commonality between a lot of post hoc methods, in that post hoc models often make assumptions that turn out to be false. So for example, some post hoc models assume that certain concepts can be linearly separated in the layer of a neural network. As one example that we see here to the right, unless the data is mean-centered, so moving it over, you can't linearly separate it. So as we can see, the same line that points at a yellow concept will point at a green concept. Post hoc methods really are suboptimal. And so that really leaves us with ad hoc models, which on the other hand are learned during training time. And due to that fact, ad hoc models do not need to make assumptions about the learned model, they can instead train the model such that those assumptions are built in. We decide to use a ad hoc model called Concept Whitening. And really, Concept Whitening avoids the problem that most ad hoc methods face because it shapes the latent space through training. Concept Whitening learns to align concepts with certain axes of a latent space. It does this after mean centering and decorrelating an input. In order to do that, there really are two stages. First, whitening, and then adding, and then learning a additional rotation matrix to align certain concepts with certain axes of a latent space. And so one example we give here is that in both A and B, the training data is not standardized or decorrelated, in that the mean is off-center and the variance along the different axes are not the same. So once we transform this data really into the shape we see in C, we can then, for example, align the green concept with the positive x-axis, and we can try to align the these other concepts with different axes. So as we said, the whitening transformation decorrelates and standardizes the data, and that happens first. In order to do this, we first calculate the batch mean, and then subtract it from the batch. And then we use a particular kind of whitening called ZCA whitening. And you can look at our paper in order to look at the particulars of how this algorithm works. But then, now that we've learned this whitened matrix, we additionally, during training, will learn this rotation matrix Q of T. And now that we've learned both of these, by learning concepts which correspond to beliefs of an agent, we can then apply this to make existing MAIRL methods more interpretable, and in addition provide guarantees as to which beliefs the network is able to learn. We're able to provide these guarantees since concept whitening only transforms the latent space and does not do backprop to any previous layers. And so that means that concept whitening cannot align concepts which were not already learned by the model in a layer. Again, all concept whitening does is standardize and decorrelate the data so that you can align it with certain axes. And if the data comes in where even after it's standardized, it's not linearly separable, at that point then concept whitening won't work. And so in this work, we choose to use the multi-agent particle environments, and these are a set of competitive and cooperative environments with multiple agents. Specifically, so far this work is focused on the tag environment, where there are 3 slower predators and 1 prey. The predators gain reward by tagging the prey, and the prey gains reward by not getting tagged. Here we have the training algorithm. MAC is trained in the same way that it would be otherwise, except that every 20 time steps, we have to update the concept whitening rotation matrix. And so this is done by passing through batches of examples of each concept and then using the result to update the rotation matrix. Again, for details, please see our paper. And then so most of my work for the past month has been to actually get concept whitening to train, and currently results are pretty limited due to the fact that whitening has substantially increased variability in training, which causes it to be unstable. And so work is currently done to bring down this variability, but as of now, it's inhibited being able to get results. So yeah, to end things off, I'd like to thank all my wonderful mentors, Professor Katya Sakara, Dr. Dana Hughes, Dr. Joseph Campbell, and lastly, PhD student Ini Yogantola, who have been really wonderful this summer, and I've learned a lot because of them. And also, really RIS would not have been possible were it not for the hard work of Rachel Burchin and John Dolan, the co-directors. They really have gone above and beyond supporting us as young researchers and really making this opportunity possible. So really a heartfelt thank you from me for that. And then, of course, nothing would be possible without money. So thank you to all of our sponsors for giving us the opportunity to participate in RIS.